All right, there we go. So this is going to be the last video for section 5.3. I want to continue talking about recursive structures, and I want to give another recursive definition of a set. This is a particularly important one that we're going to work with later in the semester. But it deals with strings, and we've talked about bit strings a little bit in the context of counting problems. But I want to give a little more formal introduction to what strings are. So strings are mathematical objects, which are basically like lists. You know, it's like an ordered sequence of elements from some set. Usually we use them in the context of like writing words or, you know, specifying like a sequence of characters. So those are the kind of words, that's the vocabulary we use for strings. We talk about an alphabet as a set from which we will draw the characters, and the characters are the elements of the alphabet. An example of an alphabet is the alphabet B, which is B stands for Boolean here. And it is the set 0 and 1. That is the alphabet from which we draw characters for bit strings, right? Bits are sequences of zeros and ones. Sometimes Boolean sometimes that set is represented as true and false, so sort of equivalent. Another common alphabet is A, B, C, D, E, all the way up to Z, right? That's the alphabet used for English words. At least it's the lowercase alphabet used for English words. Here's another one of my favorite alphabets here, this one. That's used for video games input, left, right, up, down, L1, R1, A, B, X, Y. Maybe you can include start in there as well. Maybe some other things, you know, there's lots of buttons on a video game controller, but those can be represented by characters, and then strings of characters from that alphabet can represent like strings of inputs from a controller. So yeah, so those are what strings are, right? And they're sort of set, you know, sequences of characters from some specified alphabet. But when you're talking about strings, there's one kind of bizarre string that you always have access to, no matter what your alphabet is, and it's the empty string. It's a little bit hard to wrap your head around. The empty string is a string with no characters in it, and it is represented by this symbol, which is the Greek letter lambda. Does it have a B in it? I don't think it does. Lambda? I think it does have a B. Oh no, I'm embarrassed now. I'm recording a video and I don't remember how to spell lambda. Yeah, it has a B in it. For a second, I was worried that maybe I was, you know, spelling it like the word lamb, but yeah, no, it does have a B. So the empty string is a string that has no characters in it. It's kind of similar to the empty set from set theory, but it is not the same thing. The empty set and the empty string are not the same thing. They just play a similar role in different contexts. So the empty string, you'll see how it works in particular when we get to this operation that you can apply to strings. Just like how we have operations defined on numbers, addition, multiplication, etc. You've got operations defined on propositions like and or. You've got operations defined on sets like union and intersection. And you have operations that you can define on strings. And the main operation we use on strings is this one called concatenation. So concatenation here. Concatenation is just putting strings together. So here's an example. If you have the string AB, and I will sometimes use quotes for strings because that is common practice in programming, put quotes around something and it gets interpreted as a string. So AB is a string. I'm just using this star symbol. Star in mathematics, you'll find a lot of times we use star as a generic symbol for an operation. If there's no other operation symbol, you just use star. And so I'm using that at the moment just to mean concatenate. It's not like a standard symbol for concatenate. It's just, you know, the generic operation symbol. So if we concatenate these two strings AB and BAB, you get this string AB, BAB. Pretty simple, right? So how does the empty string work? The empty string is a string that when you concatenate with other things, so say you concatenate the empty string with the string AB, you get is nothing followed by AB. So lambda as a string is like nothing. It's no characters. It's a string of length 0. It's the only string of length 0. So it has the effect of not changing whatever you combine it with. And this works in either direction. If you say AB and then concatenate with lambda, you get AB. So concatenating with lambda has the effect of, that's an effect similar to multiplying by 1 or adding 0. In fact, what this is telling us here, and this is just an example with AB, but you can do this with any other string. Lambda is the identity element. It's the identity string with respect to the concatenation operation. Concatenation. Fun word to say. I sometimes have trouble spelling it. So yeah, so lambda is like, multiplying by 1, right? Okay, so with that introduction to strings, some of the vocabulary around strings, the idea of the empty string and the operation of concatenation, with that in mind now, I want to give another example of a recursive structure. So we're going to do a recursive definition. So let's let A equal the set ABC, and let's have that be an alphabet. So saying that's an alphabet doesn't actually mean much. It just basically is indicating that we're going to take this set and use it as a set of characters for strings. That's all. So saying that it's an alphabet, that doesn't have any like special mathematical meaning. It's just a set. You can use any set as an alphabet, right? That's all. All right, so now we're going to define a set which we're going to call A star recursively by the following. Base case, lambda is an element of A star. Okay, the empty string lambda. Lambda will always represent the empty string. Okay, lambda is an element of A star. And then the recursion rule, like other recursion rules for defining sets, it's going to take the form of an if-then statement. If W, and here we're using the letter W to represent like W for word. Sometimes a string is called a word because a word is like a bunch of characters strung together, right? So word can be another word, another way to say string, basically. So if W is an element of A star, which gives you a hint about what A star is, okay? But if W is an element of A star, any element of A star, that's already been established, right? Because we're going to be applying this recursion rule successively over and over. So if W is something we already know is an A star, and X is an element of A, the alphabet, so X, so whereas W is a word, X is a character, right? Then we will say here that WX, which represents, this is just, here, the concatenation operation. And concatenation, I was using that star earlier, like as a generic operator symbol, but often we just do juxtaposition, kind of like how we write multiplication just by writing the numbers next to each other for the variables. So concatenation is written like that as well, where it's just this thing and then this thing, right? Put them together. Like you don't need to write a symbol at all. You just put them next to each other. So that's indicating concatenation there, and that is going to be found to be an element of A star as well. So those two things, that is our recursive definition, and so let's explore this definition and figure out what this set A star is going to look like. So let's apply the recursion rule step by step. Starting off, before we've applied the recursion rule at all we know is that lambda is an element of A star. So we've so far just have a set containing the empty string. So A star, remember, like like every time we're defining a set recursively, we're going to sort of build it up step by step by applying the recursion rule over and over. And the set isn't any one of those. So like this is not A star. That's a subset of A star. A star will be the sort of result of doing it forever. Like it's kind of the limit you get after applying the recursion rule infinitely many times, so to speak, or yeah, not exactly infinitely many times. This is really kind of like a hairy distinction. It's not like you can't have you can't ever do it an infinite number of times, but you can do an arbitrarily large number of times. So any element you can get by applying the recursion rule any finite number of times is going to be in the set. Okay, hold that thought because we'll talk more about that later. Let's just continue with this demonstration. So we're going to apply the recursion rule, and the first thing we can do with the recursion rule is take a W from A star. So at first, with the first time we apply it, the only string that's available to be W is our empty string lambda. Okay, so W equals lambda. So we're going to take lambda, and then we're going to concatenate it with any element of the alphabet that we want. So I can choose any element to be X. X could be A, B, or C. And so I'm going to do this 3 times. I'm going to do lambda A. Lambda A equals just A. And so A is going to be an element of A star. Okay. I can also do lambda B, which is just B. That's going to be an element of A star. Or I could do lambda C, which would be just C. And that is going to be an element of A star. So now my set so far is going to be lambda, like I had before, but also A and B and C. So I have 4 things in my set now. So next time I apply the recursion rule, now these are all possible elements, possible things that we can use for W. So we've already done it with W equals lambda, so I'm going to skip that and just have W equal one of these 3. So W could be A, B, or C. Now X has to be an element from the alphabet. So X, the choices for X are always going to be A, B, and C. So what we're going to get here is we're going to get things like AA or AB or AC, right? So choosing W equals A and then choosing X to be A, B, or C, we get those 3 strings. Then moving on, you can choose W equals B and then have BA or BB or BC. And then choosing W equals C, you could get CA or CB or CC. And so now our set contains lambda, A, B, C, and then all of those. Take these things and put them in there. I'm not going to rewrite them because that would kind of take a long time, but you get the idea, I think. So it contains all those. So what we have, basically, what we're doing here is we are essentially constructing all possible strings using characters from the alphabet A. And so before we apply the recursion rule, we just have the empty string, and then we get the empty string along with all of the strings of length 1. And then we get the empty string along with all the strings of length 1 and all the strings of length 2. And I think what you can guess is after we apply the recursion rule again, we're going to take all those new strings we just got, which are strings of length 2, and we're going to concatenate one more character on the end in all possible ways. And we're going to get all the possible strings of length 3 as well. And so every time you are applying the recursion rule, you're getting more strings. So the result here is that A star is the set of all possible finite strings over the set, the alphabet A. It is a set, but I'm just going to call it an alphabet because in this context, that's like what you call it, alphabet A. Yeah, so that's what it is. That's the result. So this is a pretty important thing. We'll discover this is important later. A star, the set of all possible finite strings over and over the alphabet A. is something we'll be using when we work with when we work with like finite state machines, and we learn about formal languages and that sort of thing. It's going to be much later in the semester, like when we get to chapter 13. Really going to be the last topic we talk about. But I'm introducing it now because it is a nice little example of recursion. So there we go.